All right. So, well, thanks a lot for the invitation, and thanks for being here. It's always exciting to discuss with interdisciplinary audiences. And so the title of the talk is Non-Equilibrium Neural Computation. I'm going to present work exploring one particular model, but in connection with ideas from models of neural networks, ideas in neuroscience, models in machine learning, and ideas from non-equilibrium physics. So the idea is to combine insights from different topics. So maybe depending on your background, maybe things that could be more outside your field, but feel free to ask for any clarification. Okay, so the motivation of the work that I am presenting today is to develop tools for understanding emergent interaction in biological networks, and specifically neural networks, and also artificial networks. And so we know that in neuroscience, but also in complex system science, there has been a tendency during the last century broadly from trying to understand complicated systems in terms of its elements, and for example, at the beginning of the century, with the discovery of neurons and the properties of the neurons, and to what even then Ramon y Cajal called the impenetrable jungle of interconnections of those neurons. So even at the beginning of modern neuroscience, there was this idea that this mesh of connections was one of the biggest problems for understanding what was going on in complex biological systems. And interestingly, it was one of Ramon y Cajal's student, which is called Llorente de No, which already in the 30s postulated the idea that it is not the components of neural networks that we need to understand, but the kind of recurrent interconnections that create that feedback the activity again back to the network. And Llorente de No realized that most of the connections in the cortex are recurrent feedback loops, and he was one of the first people to bring this idea of a feedback loop that then was key in neuroscience, in cybernetics, and the development of to the current complex systems and systems science. And the idea that this kind of feedback loops will turn into reverberation. So reverberation or self stimulating activity. So he had this idea that most of the connections in a cortex, in a brain, had the structures that look like this, what he called a reverberating chain, in which the activity in some neuron is fed back into a feedback loop that eventually comes back to the original point. He hypothesized that this kind of the discharge in this kind of loops constituted the autogenous activity of the brain. And so he provided the first biological evidence for the existence of this kind of feedback loops of self-excitation, and he brought the idea that this kind of structure was the building block of neural organization, and not the neurons, but this small or these blocks of dynamical recurrent activity. This idea then influenced a lot the cybernetic community, and it's interesting that Llorente de No was very actively participating in the first meetings of the cybernetic community with Wiener and McCulloch in the 40s, and in the first Macy conference, which is considered the official birth of cybernetics and the science that led to modern artificial intelligence. This Macy conference was inaugurated by a joint lecture by John von Neumann and Llorente de No. And so, and a few years later, the term cybernetics was coined by Norbert Wiener, and yeah, this led to the inception of many scientific fields, from artificial intelligence to complex systems, and so on. So, and also interestingly, this idea also influenced the work of Donald Hebb, which also was aware of the work by Rafael Lorente, which postulated this cell assembly hypothesis, like trying to think of how this kind of recurrent connectivity could be created in the brain. He postulated this idea of what is usually called Hebbian plasticity, or cell assemblies, in which the way to create these complex networks of circuits is just to reinforce the connections of cells that are active at the same time. So the idea is that if two neurons fire together, they will strengthen the coupling between both of them. And by experiencing repeated stimuli, we could create the network architecture sustaining this kind of neural activity in an emergent way. And so Hebb had this idea that once you have this kind of connectivity, you had these assemblies of neurons or cells that are activated at the same time, and the sequential activation of these cell assemblies will constitute what's behind of the dynamical organization of a brain. So he was trying to create this kind of maps in which the activation of one assembly led to the activation of another. So there was an intrinsic, like, dynamical component to the behavior of these circuits. And a bit later, in the 80s, John Hopfield, which just received the Boltzmann Medal this year for this and other works, proposed this idea of the quite popular idea of a neural network model, which has become quite popular, which are Hopfield networks, in which he tried to formalize this kind of idea of how to create this neural network architecture from a point of view closer to statistical physics. So he took Hopfield, Donald Hebb's idea that neurons that are activated together or are activated during the same stimuli create connections together, and so he defined the connections of the network according to this overlapping of activity of one external stimuli. And there one assumption, which is that one simplifying assumption, which is assuming that the connections between neurons are symmetric. And when you do that, this model becomes something similar to the spin model, to spin models or the Ising models in physics. And so we can define some energy function that describes which are the most likely states of a network. So this is a way to connect all these intuitions to a formalization that can be studied using the tools from physics, which is really powerful and has been tremendously influential in computational neuroscience or in machine learning. And this model is widely used in all these fields, even if it's a very simplified model. And so roughly the idea is that we have these connections between neurons, and these connections are defined as a superposition of different patterns. For example, we can imagine a neural network, which is just a grid, and we can think that the patterns are, for example, some letters, some images in this grid, for example, these letters. And the idea is that imposing these patterns into the connections of the network is able to retrieve some patterns, so this works as associative memory. So just to show you one example. So imagine that we have two patterns like this. So we show this, we train the network so that it's encoding these two patterns. And for example, we can give the network some noisy patterns. So this is a letter A with a lot of noise. and if we let the network run, it will retrieve the original pattern. So the idea is very simple. And so by being able to encode these patterns in the network, oh, sorry. Second. We can, so we can think of networks that are able to retrieve memories or retrieve different patterns that have been encoded. And we can, for example, use this to create very simple machine learning models, for example, encoding images. Okay, so, and the idea is that we have a physical representation of this kind of models, in which we have defined this energy function that depends on all these patterns that we have encoded. And the rough idea is that we can, encoding the patterns in this way creates a minimum in some energy landscape, and we can think of retrieving the pattern as having some noisy starting point. For example, here, I don't know if you can see my cursor, and letting the system run down towards an energy minimum, which is some kind of attractor of this network. Okay, and this can explain in a simple way how networks can learn patterns and retrieve them. But still, something interesting to notice is that if we think in terms of physics, of statistical physics, these are the objects that are in equilibrium. So in the sense that we can start that in some point here, which is out of equilibrium, and the network will go towards the point of minimum energy and stop there. So somehow this is a static model in which time plays no role. Okay. And in terms of statistical physics, well, we can this corresponds to a point of maximum entropy in which parameters are related with conservative variables, if you are familiar with ideas in this case. And there has been a lot of interesting work with this kind of models, for example, in neuroscience. So this model, it's usually a model of binary variables in the simplest case. So it can be applied straightforwardly to model activations of neural spikes. We can record the spikes from biological neurons, like these spike trains, and codify them with zeros and ones, and try to fit the parameters of the model that best reproduces, for example, activity recorded in the lab, no, in vitro data. So, and then we can study these models from the point of view of statistical physics, and we can compute how much of the variance of biological activity. We can think what kind of parameters do we need to capture the phenomena that happen in the lab, or what kind of effects or what kind of mechanisms may be behind the coordination of neurons. And there has been this interesting studies trying to connect ideas of self-organized criticality in the brain with these kind of models, in which we can connect the behavior of the models with phase transitions, or study the phase diagram of such models, and have a much more deeper knowledge than we can get from just data analysis, no? Because in this case, we have a model that also describes in a way the mechanisms that are generating the patterns. So we are not only studying the patterns, but also have a connection with the plausible mechanisms. Okay, so far this is quite interesting, and there has been a lot of interesting research in this direction. But in many cases, when we are thinking of networks that encode patterns, we are not just interested in this kind of static picture in which we just have a pattern and the system stays there or stays in some equilibrium. Usually, when we're interested in biological phenomena or cognitive phenomena or intelligent behavior, we are interested in behavior that takes the form of sequences. No, or we can think, for example, in language models. We have the system has some previous history, which is, for example, the beginning of a sentence, and we want to predict what's the next word or the next token. And so we can think also any tasks like object manipulation or perception, or just the dynamics of any complex biological system, in which past future order is a fundamental aspect of the behavior. And so far, the models that I have described cannot capture this kind of temporal order. Okay, and this was already noticed by Rafael Lorente, which hypothesized that in this kind of chains, the time relation between within the chain, so the time that it takes this signal to be fed back inside the neuron that generated it, it's what allow that generate the structure of autogenous activity in neural signals. So somehow it's the structure of these feedback loops that generate some dynamical order. And this was also noticed by Norbert Wiener. And if you look at his seminal book on cybernetics, he devotes the first chapter to discussing the idea that the kind of dynamics that we have in biological and also artificial intelligence systems is the dynamics of out of equilibrium systems, which are systems in which we have something called irreversible dynamics, meaning that the dynamics going forward in time are not the same that the dynamics going backward in time. And so in physics, this is usually illustrated by the idea of breaking a cup. So I can have a cup, and if I just lift the cup up and down, my actions are reversible in the sense that the potential energy that I used to lift the cup, it's can be released by just doing the opposite movement. No, in the sense that so we have this these conservative properties, which make any action reversible. But if I smash the cup against the ground, against the floor, the bonds that hold the cup together break, releasing heat, and this makes this action irreversible in the sense that the energy that I have used to break the cup, it's much smaller than the energy that I will need to get all the pieces and bring the atomic bonds together to create the original object, because this energy is lost because it has been released in the form of a small amount of heat created when the cup broke. So we can think of this difference between reversible and irreversible actions and try to think what this means, for example, in the activity in the case of activation of a neural network. So if we think of, for example, modeling this kind of spike trains, this means that we need to have models that not only capture the correlations at a given point, but the correlations between this given point and the previous activity. And this takes the form of these correlations in which one neuron at time t interacts with the states of the previous neurons. And this make these connections as potentially asymmetric, in the sense that this connection Jij can be different from Ji. No, and in the previous case, so if you notice here, so here they are symmetric, no, because if I reverse the order, the parameter is the same. Okay, so what happens when we allow this asymmetry? So we saw that in the symmetric case, we have some energy landscape, which looks like the picture in the left, in which we have some minima, which can encode different patterns. So, and if you start close to this minimum value, you will go down and stay there, and nothing ever changes. However, when you have this asymmetric connectivity, you can have things like the picture in the left as well, but you can have more interesting structures like the one in the right, in which we have this loop of activity in which the system is continuously oscillating oscillating here. So if we think in terms of encoding patterns, now we, instead of just having some static patterns, some letter, we can have like some kind of video showing images in a specific sequences. For example, writing a word in a specific direction, right? We can have some things like this. We can have more things like encoding many loops at once, or having chaotic activity traveling around around some landscape. And this idea has also been explored in different ways, in thinking of neural networks or biological networks. And we saw that things like something similar to this was already present in Donald Hebb's work. But also there's, for example, this idea of chaotic itinerancy. For some time, it was discussed, this idea of cortical zones, the idea that the cortex can reproduce certain structures in a given order with somewhat a lot of precision, although this idea has been debated, and also the methods to employ to prove it. So somehow this thinking about now the brain as structures that encode this type of dynamic patterns, it's been influenced, but it's been increasingly influential, although we don't have developed as much the tools, this kind of tools inspired in physics to understand it. And so the goal of this talk is to try to study how the intelligent behavior shaped by these recurrent interactions can generate this adaptive neural activity in a sense. And so we want to study this type of neural network models connected with ideas of computation, with ideas of non-equilibrium physics, and so on. And so to give you an idea, I'm going to talk about one specific paper that we published some months ago, in which we try to study a model similar to the Hopfield model that I was explaining before. Okay, so when studying this kind of Hopfield models, so one question that was attracted a lot of attention is how many patterns can a network store? And we can use tools from, so imagine that we have a letter like before, but we want to have a model with more and more memory capacity as the size increases. So what's the limit? No, and there is we can use methods from coding theory, or we can use to compute the number of patterns that can be stored, or the number of bits that can be stored, or we can use methods from statistical mechanics, like the replica methods used to study spin glasses, which are very similar to this kind of neural networks, to calculate how many patterns or how many minima can be stored in a network. And so the question here will be not only how many attractors can a network have, but how many dynamic patterns can a non-equilibrium network or this kind of asymmetric network store. So we think of these cortical zones, no, like how many zones or how many sequences a network knows. A way to calculate it in terms of information theory, it's to recur to information theory of non-equilibrium systems, of systems that have a specific direction in time. So to illustrate the idea, you can think of, for example, having a box of dice. So imagine you have a box with these dice inside. You look into the box, you shake it, and you look again. And you can think, what's the state before shaking it and the state after? And obviously, the state before is the one on the right, and the state after is the one on the left. And this is so this is this idea of the laws of thermodynamics, that entropy can only increase, disorder or uncertainty is always more likely that certainty in systems under fluctuations in isolation. No? So this creates, so somehow this change of entropy, this change of information, so there is many ways, much more, it's more, many ways in which we can have a disorder like the one in the left, but there's very few ways in which we can have order like the one in the right. So this increase of the uncertainty, or this increase of entropy, which can be measured in terms of bits, defines this direction in time. So can we have a general description of this kind of phenomenon? So, and this has been developed in the study of non-equilibrium systems, and the field that has been developed in the last 2 decades or so, which is usually called stochastic thermodynamics or thermodynamics of information, which try to describe out of equilibrium systems that resist these tendencies to increase disorder by dissipating entropy to the environment. So we can have systems that are somehow interacting with something outside or have this kind of recurrent loops with asymmetric behavior. And these systems can impose structure in their dynamics by dissipating entropy to the environment. No? And this is something that happens in every biological system. No? You need to feed, to eat food, you dissipate heat. And in order to maintain your dynamical activity, you are continuously, you have to continuously keep yourself out of equilibrium, resisting this tendency to increase entropy, which will lead you to death. And so since the late 90s, there has been like different theorems that have started this field trying to connect this entropy dissipation with ultimately with quantities that can be measured in terms of information. And one key development was a Crook fluctuations theorem, which shows how this dissipation of entropy that allows you to maintain some intrinsic order structure, it's connected to temporal time irreversibility. You know, again, this idea of sequences having one specific direction in time. And particularly, this irreversibility is measured as a Kullback-Leibler divergence between the probability of observing one trajectory forwards in time versus the probability of observing the same trajectory in the reverse direction. Not like observing one movie going forward, and how weird or how strange will be the same movie in the reverse direction. And this can be measured in terms of bits. So we have a direct interpretation of this kind of phenomena in terms of information. So we have this link between this idea in physics of being out of equilibrium with something we can measure just in terms of information. No? So this is to give you an intuitive idea. So this idea of irreversible time was explored in Christopher Nolan's movie Tenet. So the movie is not super interesting, for that the plot is a bit dumb, but has this idea of what will happen if we could reverse the direction on time. So and the idea is that some of the characters in the movie can reverse time and travel backwards in time, and for them everything is super strange. You know, the cars are traveling backward, they shoot a gun and the bullet is going back inside the gun and things like that. No, and so for these characters, everything is super surprising, no, because things don't work as usual. And this amount of surprise measuring bits is this idea of measuring of quantifying entropy production, quantifying how much information it's encoded in your dynamical structure. Okay, so we are trying to measure this idea of entropy production, to measure this amount of dynamical irreversibility in bits in neural networks, and try to understand what it implies for the behavior of a neural network. So we are not the first ones to explore this idea. Interestingly, in neuroscience, during the last couple of years, there has been a growing interest to try to understand what's the role of irreversibility in the brain. So you could try to measure brain dynamics. Well, in general, to do this computation is quite hard, but you will have some simplified or lower dimensional representation of time dynamics. And you could think, okay, it's the structure of the human brain or other brain showing dynamics that are irreversible, that have some specific direction in time. For example, are they oscillating in one direction, or are they close to being reversible, close to equilibrium? And the answer is that it depends on the task. If you are resting or you are doing tasks that do not involve a lot of cognitive effort, generally your macroscopic brain activity is close to reversible. But if you are doing tasks that are more demanding or involve some level of interaction or complexity, your brain becomes more and more irreversible. And this is interesting because so we know that as biological systems at the macroscopic level, we are very irreversible. We are dissipating a lot of entropy. But these studies show that not all this entropy dissipation is translated to the macroscopic level. So it's interesting that as a macroscopic system, we need to bring this macroscopic irreversible into this macroscopic level to do some things in the world. And this is connected to the idea of Wiener that intelligent systems need to exploit more and more irreversibility to be able to interact with the world. So this is a study by Chris Lin and Daniel Basset and other collaborators. And there has been also studies trying to connect irreversibility and this entropy production with states of consciousness, showing how being conscious, as in compare for example, with being in unconscious sleep, has a higher level of irreversibility, or also compared with different anesthetics. And also there has been some studies trying to connect a difference in neuropsychiatric diseases like schizophrenia or ADHD with a reduced level of irreversibility in brain dynamics. So all these studies are starting looking into this question, but they also suggest that irreversibility is playing an important role in our neural organization. Okay, so this brings the question of so how entropy production behaves in large neural systems. And so many, we have many models of neural activity. We have also models describing the non-equilibrium dynamics of neural networks, but we don't have much showing how irreversibility or entropy production behaves in this kind of large system, mostly because the biological applications of stochastic thermodynamics and characterizations of entropy production have been focused in small biological mechanisms, and there is not that much about what happens at the network level. And one reason for that is that in general it's not easy to study these stochastic thermodynamical properties of large systems. So we want to understand what kind of regimes we find in non-equilibrium neural networks. So we studied that together with Hideaki Shimasaki in Kyoto University and Masanagi Garashi in Hokkaido University. And after, so it was an article that took a long time to do all the analytical study and mathematical study. We came with an article trying to describe the entropy production in a class of neural network models when the size of the system tends to infinity. So this was published a few months ago in Nature Communications. So the idea is that we have a neural network model, which is very similar to the Hopfield models I was describing before, in which the activation of neuron at time t depends on some sigmoid function with some asymmetric connections to the state of the network in the previous state. We studied the model both under synchronous dynamic and asynchronous dynamics, in which all the states either are updated all at once or sequentially. And again, when the connections are symmetric, the system has this equilibrium structure with some attractors, but when the system is asymmetric, it can have complex dynamical activities that it's out of equilibrium. Okay, and so we studied a version of the model which is similar to a spin glass, in which the parameters, the couplings are stochastic and disordered. So the values of these connections here are described by some Gaussian distribution. Here, these are we define random parameters according to this Gaussian distribution. So in the case of symmetric connections, this is a spin glass, and we studied the case of asymmetric connections in which Jij is uncorrelated with Ji. And so if we do simulations of the model, we find that there is some different regimes of behavior. So basically, we have two parameters. One is the inverse temperature beta. When beta is very small, the system is very random. And when beta is large, the system becomes more closer to the deterministic behavior. And then we have this other parameter, delta J, which is the level of disorder in the couplings. This is the variance, the standard deviation of these random connections in the network. So when the temperature is, when the inverse temperature is very small, the system is very random. We have something like the top left. And when the disorder in the connections is small, but we have this large value of beta, the system is very deterministic. So the activity goes either 2 + 1 or -1. So the system is polarized, and we have this kind of bifurcation. And in the middle, we have a critical point, which looks like the bottom left, in which the system is somehow between disorder and disorder. So this is the usual critical phase transition behavior. However, if we go to the state of large beta, so very deterministic behavior, and large delta J, so the system is very disordered, we have some different behavior. In equilibrium, this will be a spin glass in a state with many minima, so a metastable system. And here we have a system that it's disordered, but deterministic, and has this kind of disorder dynamics, which behave in a chaotic-like manner. So instead of a spin glass, we have like this sort of quasi-deterministic chaos that we will study later. Okay, so we have a system that has all these different regimes of activity, and we want to study it mathematically. And for doing that, we have to resort to methods in out-of-equilibrium statistical physics. And we don't have a free energy or that can describe the equilibrium the distribution of the system. So we can study the probabilities of different paths. And calculating these probabilities, we can measure the entropy of paths. And with this entropy and comparing the entropy of paths forward in time versus the entropy of paths going backwards in time, we can compute this entropy production, quantifying the irreversibility of the system. So how much information is encoded in the forward paths compared to the backward paths. Okay, so in general, so I'm going to explain this a bit quickly, but you can ask later or take a look at the paper. In equilibrium statistical mechanics, we will define a free energy and try to calculate it in the thermodynamic limit and calculate the statistical properties of the system from there. And this is an equilibrium system, so we don't have a free energy. So we define a generating functional, which is an object that behaves as a free energy, even the system does not have one, in which we calculate the average of this exponential here. We calculate the average of the path, so we can think of this as some path integral. And we introduce this virtual parameters J, which can retrieve the statistics of the system as in the same way that we do usually with the free energy. Okay, so we have this kind of network. We have this quench disorder of the couplings. And as usual in physics, we calculate what's the average behavior integrating over this disorder of parameters, these Gaussian couplings. So we have this generating functional, which behaves as a free energy. And in equilibrium, we will use some trick like the replica method. And in out-of-equilibrium, we can use similar methods like the path integral methods to calculate this generative functional. And so in equilibrium, we assume that we have many replicas of the system, and integrating the disorder, we substitute these couplings between neurons or spins in each replica by self-couplings between replicas, so we get some mean-field solution. And in this out-of-equilibrium case, we have couplings in time and averaging over the disorder. We change this couplings by self-couplings in time. So again, we have simplified the system, and these complicated connections integrating over the disorder can become the self-couplings as we do with the spin glasses. So if you're not familiar with this, you can just believe this. And yes, so these are just tricks to calculate a simple solution to describe the behavior of this disorder disorder complex behavior over many parameters. So we are doing this. We are able to obtain an analytical solution. Well, we obtain two order parameters of the system, this M and Q, which describe the average magnetization and couplings in time, like this self-couplings in time here. And we are also able to bring an analytical description of what's the level of irreversibility, what's the entropy production of the network in the limit of infinity size. And we can do that for parallel updates and as well as sequential updates. And we get these expressions here. Okay. So if we analyze the order parameters, we find the usual order-disorder phase transition. We have a paramagnetic and ferromagnetic states, and both M and Q, the order parameters undergo this transition. But we don't have an equivalent of the stained glass phase, which will be located in the top right of this phase diagram. Okay, so this is strange. So we don't have, there doesn't seem to be a phase transition between the disorder, random behavior, and the stained glass, which would be in the top left. But if we analyze the entropy production, which is the figure in the right, we find that there's a difference between the random in the bottom left. So well, basically, when we are in the disorder side, which is in the left, or in the order side, which is in the right, the entropy the reversibility is very low. But if we cross the critical phase transition, which is the white dashed line here, we find that the entropy production peaks at the phase transition. So this critical behavior will be the state of more irreversibility for a given value of disorder delta J. And also, if we go to the top part, we find that also the level of irreversibility is very large here to this region, which looks like the disorder region according to the order parameters. So the order parameters don't change, but the entropy production, the irreversibility changes a lot. Okay, well, we tested the behavior with numerical simulations, and we see that both the order parameters and the entropy production converge to the theoretical values. So just to test our solution. And okay, and we are able, so with this idea of how many patterns can the network encode, we can calculate which is the number of periodic patterns that the network can encode, and we find that this has this Poisson distribution, which roughly depends on the value of n. So both here, so in the top, so basically here in the other side we will have very few dynamical patterns, but here in the yellow side we will be able to store many and many. The system will show many dynamical patterns. So just to give you an idea of so what are the different kinds of behavior, we try to study these visualizations of the network in the deterministic regime. So we have this disorder phase, we have disorder phase, and we have this critical point in between, and we have in the top right this point of quasi-deterministic chaos. So if we look at some point here with large beta, so the system is very deterministic, and we are here, we find something like this. We have patterns that are very simple. So this is a very small network, just 25 neurons. And so here the behavior will be in the order side, so it will be quite boring. But if we go to the critical point, we will have a very flexible point between disorder and these patterns that are encoded in the right. So this is the x-axis is time, and these are the state of the 25 neurons. So here we will generate a reversibility and complexity by very flexibly combining these patterns. So this will be this critical point here. And on the opposite, if we look at this quasi-deterministic chaos, we look at the large beta range, we find something like this. So all these are different realizations of the behavior of one network with different initial states. And so we see that depending on the initial state, the network falls into some attractor, which can be very complex. So here, so in the middle, we see this one, which has a shorter period. And this one, for example, in the top, we have one with a quite long period. So somehow we see that in this regime here, the network is able to store many possible different dynamical patterns that are always repeated in the same sequence. So compared to the behavior here, which will be a very flexible combination of many patterns, here the system is very inflexible, but it has a very wide range of dynamical patterns of activity. And the number of these patterns can be encoded with the result that I was showing here. So somehow this gives an idea of, so if we think that irreversibility is an important part of neural activity, this model shows that in this simplified neural network, even if it has a non-trivial behavior, we have at least two ways to generate very irreversible behavior. One will be to be near a critical point with with these intuitions of the brain being near a self-organized critical state of self-organized criticality, of being something between order and disorder, and having this flexibility to combine structure patterns in a very flexible way. And the other possibility is to have these hard-coded sequences that are always repeated in the same order. So something like these cortical zones. So we see that these kind of results of trying to capture the thermodynamics of phase transitions and large neural networks can give us an idea of what are the possibilities, for example, to generate these irreversible patterns in neural networks. And this tells us that maybe in these experiments in neuroscience, we do not only need to measure this irreversibility on entropy production, but we maybe can also measure other quantities like this path entropy forward and backwards that can give us an idea if we are in a critical point or if we are in this quasi-deterministic chaos, for example, no? And this will give us a richer picture of brain organization. So just to conclude, we have proposed this method of using path integrals over a method described in terms of statistical physics of out-of-equilibrium systems that can give us an idea of what kind of dynamical structure we can see and what's the role of irreversibility in different regimes, and what kind of variables we can use to identify what it is that we are observing, for example, in data. So there is so this is a first step in this sense, but there is different directions this will take. We can there is work to propose more refined methods of irreversibility, for example, trying to compute how much of this irreversibility is some emergent property of the network and not only a property of components. For example, you can think there is very trivial systems that will dissipate a lot of entropy, like for example, the engine in your car. But and we want to understand irreversibility that is related with the emergent organization in a system, and there is mathematical methods to capture this. Or there is also like this idea of irreversibility related with relaxing to equilibrium versus irreversibility that is intrinsic to a system. So this is a very active of research in statistical physics, and there is a lot of mathematics being developed to develop more complex measures. Also a new line that we are working right now with Angel Pog, one of my students, is to try to apply these methods to models in artificial intelligence. Specifically, transformer models have a behavior that is very close to this Hopfield network. So we want to understand better what are the possible dynamical structures that we have in attention mechanism, attention layers, and transformers, to try to have or what's the level, what role irreversibility plays in this kind of systems, to try to have some insights from a physical point of view in what is possible with networks like this. And so the idea is to have these methods and models that are inspired by physics, and to try to have better descriptions of what kind of dynamics or what kind of or models that exemplify what are the principles that drives these systems and what's possible and what's not, and how reversibility or entropy production or being out of equilibrium, or what are the physical limits of computation in this kind of systems. So okay, so this is the paper if you want to take a look, and this is yeah, so it's a first step in this direction, and we want to try to explore more connections in yeah, applications of this with biological data, with machine learning models, and yeah, so feel free to ask any questions. Thank you.
Thank you very much, Miguel. There are two questions in the Q&A
yeah, thanks,
from
Miguel.
Nishal. Let me allow Nishal to talk so he can maybe ask them in person. He raised his hand.
Perfect.
Hi, is it working?
Yeah.
Yes.
Okay. Thank you for the great talk. I had two questions. One was before you went to the dynamics, which was understand like this result you mentioned about how the kind of max entropy model explained various neural code or neural behavior. So like, what is the source of this max entropy behavior in neural networks? Like in physics, we have like whatever second principle of thermodynamics or something that gives you the max entropy. Why would there be max entropy like thing in neuroscience? And the second question was, you mentioned something about analyzing transformer, but transformers are not recurrent networks, at least in practice, like Hopfield or like neural networks in the brain. So what sense of dynamics were you talking about?
Okay, thank you. Yeah, these are good questions. So let me show you. Yeah. So if I understand correctly, so the first question is why do we expect so this kind of Hopfield models to behave as maximum entropy models? Is that right?
Especially in context of neuroscience, you showed some figures where the neural data kind of seems to admit to this point of views. And why would that be? What is causing the maximum entropy behavior in neural networks in the brains, for example?
Okay, so here so these kind of models are maximum entropy just because they are parameterized in a way in which you can define the state of the model by a conservative quantity. So you have this energy, which is described as the symmetric connections. So this is an assumption that it's quite unplausible, not that neurons are connected symmetrically.
Yeah.
And so if you run like simple dynamics on this energy function, you will reach a probability distribution that's defined by this energy. All right, and so you could have a model like this and have some observations and just fit the parameters of the model to be close to some neural activation. So what it has been found doing this kind of experiments is that if the system is not too large, having a model with just single and pairwise interactions captures relatively well the behavior of the system. And this happens if you have like a few tens of neurons, like 20 neurons, things like that. Okay, but if you try to analyze larger systems, usually these pairwise maximum entropy models are not very good. They are not very good at capturing higher order correlations, like correlations between groups of 3 neurons and things like that.
Got you.
Okay, and so why this model? And there is papers trying to add more interaction terms in this energy function here. So you will add other parameters that stand for collective interactions, so interactions of groups of more than 2 neurons. Okay.
So I should take it as more of a fitting model, like it's to fit the data rather than making some like almost ontological claims about what the neurons are actually doing.
Exactly. So if you add enough parameters, you could basically fit any probability distribution, right? But the important thing here is that this is a probability distribution of finding one pattern in one state of time. But this doesn't tell you anything about the dynamics. No, like having a model of the dynamics is much more complicated, and it's in general it's a very difficult problem, and there is some work, but this is something that we don't know very well how to do successfully. All right. So here it's okay. Given some previous activation, what will be the next pattern? So this is a much more difficult problem, but also it's one that potentially can tell you more about the mechanisms.
Right.
Because here we only care about characterizing the probability of this pattern, but we don't care about the order. We don't care about the dynamics.
I see.
Okay.
And so one more question then. The dynamics analysis that you guys did, like what in addition do we get compared to like the dynamical mean field theory that Heinz and like other people had around like that was a replacement for replica method. They seem to be tackling the same kind of problem of like looking at the spin glass problem dynamically. So here, is it that you guys are additionally computing this entropy production?
Yes, so there has been some studies with some cases of out of equilibrium spin glasses, and there is some we already knew, for example, that there is no spin glass phase there, and that we have some kind of disorder. But so we knew about for example the kind of order parameters of the phase diagram, but we didn't know anything about the entropy production. So this is being able to calculate it, this is a new contribution.
Okay.
And also, so the second question was about transformers. So the idea is that so there's different works. There's a short review that came out this year in Nature, I think, or it's called A New Frontier for Whole-Field Networks by Krotov. So there is this work trying to describe the output of a transformer model or attention layers in transformer as some kind of whole-field networks. And as you said, this is not a feed, it's not a recurrent network, but you can think of it as some feed-forward network that will generate the next token. No, but you can think, but still, like you could think of the system as something similar, no, in the sense that so you have some history of tokens, like some words that are before, and you have a network that generates the next state, which is a vector encoding the next word, for example. And then this is fed back again into the transformer and generating the same. So in a sense, so it's not the same, and it's it's not trivial how to turn this into a transformer, but the problem will be similar to this, like having tokens that are embedded are captured by a vector, and thinking of what's the architecture that generates the next state of the sequence.
Yeah, gotcha. That makes sense. That was what I assumed too, but just wanted to make sure.
Yeah, but still, the process of going from the green part to the red part is a few feed-forward calculations, right? And the idea is that maybe you can,
but would the same kind of methods work? Because there are like these long-term temporal dependencies in transformers, unlike like Markov like dynamics.
Yeah, exactly. So here you will need dependencies with a long window.
Gotcha.
And so right now we are trying to have like toy models of attention layers and having like a short window, but instead of just having Markov, trying to calculate, what would happen with a longer window.
Cool. Thank you.
Yeah, you're welcome.
Let's see. Guillaume has a question.
Yeah, can you hear me? Yeah,
Yep.
Yeah, cool. Hi, Miguel. Yeah, can you say a bit more about this emergent non-equilibrium computation? I think you mentioned higher order entropy term, because you talked about in your talk about the time irreversibility using entropy. So are you also thinking of extending this work by using some sort of like information decomposition and then looking at higher I don't know. Yeah. So what does it mean even, like the emergence of higher order time irreversibility there in that case?
Mm-hmm. Okay, thanks. Yeah, we went over this quite quickly, but yeah, this is a super interesting discussion. Well, so first, so we have this kind of no-phase diagram with entropy production, and we want to understand how having a high degree of irreversibility it's connected with the ability of, for example, encoding many different dynamical patterns. And what we see, so this is still a work in progress, but what we see is that along the critical point, we are able to capture the structure dynamical patterns, and here we have a lot of irreversibility, but these are like random like patterns, no? And like in general, so we know that biological systems, we know that biological systems are very far from equilibrium. Your brain is dissipating a lot of entropy continuously, no? But what you see, for example, in this experiment is that, so when you are resting, all this entropy dissipation, so probably when you are resting, your brain is dissipating roughly the same entropy that when you are thinking very hard. But somehow this irreversibility is lost when you are resting. No, it doesn't translate to the macroscopic level. So we want to understand, okay, what's we are thinking, so how to understand when this dissipation is translated into complex macroscopic structures, no? And as I was mentioning this example, so you could have like very trivial systems that dissipate a lot of entropy and are very reversible, no? You could have like an array of motors, and each one is dissipating a lot of entropy, and the joint system is dissipating a lot of entropy, no? But this doesn't mean that they are doing anything intelligent. So there is a couple of proposals to decompose entropy production of a joint system into the components plus some other terms. So we could think, okay, the entropy production of a system with two parts is the entropy of one part plus the entropy of the other, and some other quantity, which is some emergent entropy production. And there is an ongoing debate about how to measure this. This work by Suzuki Ito, and also a recent paper by Chris Lin with different proposals. And in a collaboration with Artem Nikolchinsky, so we published a short abstract about this in the Artificial Life conference, trying to think of this problem in terms of information geometry, and think of this decomposition in terms of projection onto information theoretical manifolds. If you are, maybe you will be interested in the paper if you are interested in this problem. This is ongoing work, and there is still no consensus in what's the correct way to do it, and it's also in general difficult to compute. But I think this is a key point, a crucial point. No, like we know since a long time that being out of equilibrium is a defining property of living systems. Like every living system must be out of equilibrium. But maybe living systems are also out of equilibrium in some particular ways, no? Ways that maintain some emergent structures. And I think understanding that will be really fascinating, no? To think we can have out of equilibrium systems like I know, a hurricane or a candle, But so what's particular about living systems? No, what's particular about the kind of structures they generate? I think this is like a very fascinating direction. No, what are the out of equilibrium systems, out of equilibrium physics of intelligent and living systems? And we don't know that much about it, but I think these kind of tools can give us some answers in that direction.
Right. Yeah. This is super interesting. So, but here, are you thinking about, for example, like calculating like the emergent boundary of an agent, for example, or are you still thinking of like, do you think like does this apply for like things like calculating boundaries, but also like higher order computation in the brain? Like, are you thinking about a similar framework for both of these things, or is this?
Yeah, that's an interesting direction. Although, yeah, you could, but yeah, still, what's the you could have, yeah, the introduction of some set of system which is a living system or you and the environment, but what do you do with the part that it's emergent from the interaction? So I think it's not trivial. So one thing will be drawing boundaries, other thing will be to identify these emergent entropy production components, like entropy production that is only generated in interaction. Yeah, I think like having toy models of these kind of things, like for example, I don't know, a robot doing a very simple task, will be super useful to try to have an intuition of what kind of process is needed.
Yeah. Ooh, yeah, no, that's very interesting. Yeah, I guess, I mean, as far as I know, one issue with, I'm not sure this was what you had in mind, but like one issue with information decomposition stuff, as you know, is like it seems computationally very intractable.
Yeah.
And so, like maybe we can do this in toy model, but then if you want to scale this up, maybe maybe we need something or like some estimates but yeah. I don't know.
Yeah. I think in part my hope is that maybe like these models where we can obtain these complicated mean field solutions could be a way to have non-trivial systems where we can still calculate some things. Like of course this is going to be impossible to apply to many instances, but maybe there is classes of models where this is possible.
Right. Yeah. Thanks.
Awesome. And we have Sahil. Let me see. There we go.
Can you hear me okay?
Yes, we can.
Hey, hi, Miguel. Thanks for the talk. I am hoping you can help me with building some intuition for the coupling heterogeneity parameter, like, and generally quasi-determinism. Like, I'm not sure if I have intuition for what order and disorder means. I have some intuition for what temperature means, but not very much for delta J.
Yeah.
And I'm wondering if you can like give me some like intuitive things to like spot it in the wild. Like it feels like you're expanding my notion of order and disorder in some way, but I'm not ready to put it into practice.
Yeah.
Looks
Okay.
exciting.
Yeah, that's a good question. Yeah, maybe I went over this a bit fast. So the idea is that these couplings have this Gaussian distribution around some middle value J0, right? So you can see this J0 as coupling elements in the network. So when J0 dominates, the system goes from this noise to this polarization. Everything goes to positive or negative, to active or inactive, right? So this will be the case in which the variance is 0 or very small. So when this delta J is larger, it means that these connections become more disordered. So like having noise. So it's just like, having some noise in the signals that go to each neuron. So this challenges this structure state, and you end up in something like this. All right. So you can think of delta J as the heterogeneity in the network connections. So if everything is homogeneous, you just have either order or disorder, either random or or deterministic order. And this delta J, even in the case where you have a very deterministic system, it challenges the having a homogeneous state. This is roughly the idea.
And the quasi is just that it's heterogeneous. That's all that the adjective quasi is doing, or is it doing more?
Sorry, can you repeat?
The phrase quasi in quasi-deterministic. You're only pointing at the heterogeneity and nothing more, or is there something more to that?
Yeah. So when beta is infinity, it will be deterministic, and this beta, for example, beta equal 4 is very close to deterministic. So here the thing is that each neuron is going to depend on the previous state with these very random connections. So its state is going to be very random, even if it's deterministic or very close to deterministic. So here the disorder comes from the heterogeneity in the connections and not from random behavior. So the randomness comes from, yeah, every neuron is very deterministic, but the randomness comes from the disorder in the couplings.
Is there a way to, like, again, I was asking more for intuition, is there a way to, like, expand this idea more in the sense of like you give the example of a breaking cup, and I can feel there's an intuitive idea of, okay, this is like towards more irreversibility or something.
Yeah.
And I'm like, now can I identify delta J and temperature independently in that kind of process, or no? Because there's not any nodes or something.
Yeah, no, you could think of a system of many components, like, I don't know, many agents. So you could have disorder because every agent is very random. Or in this case, you could have agents that are not random, but the behavior of every agent is very different. So you have a disorder because every component is very different.
So it's a kind of richness.
Yeah, something like that, like richness of behavior of the components, no? Which in the so it's like two different ways of generating disorder. One is being stochastic and random, and another is like having a very wide range of behaviors, like a very rich repertoire of behaviors of the components of the system.
Right, thanks.
All right. Do we have any other questions? Once, twice, 3 times, and that's all. All right. Thank you very much, Miguel, for your lovely talk. Thank you, all the attendees, for coming and for your questions. And this has been the latest so far speaker series. Hope we see you again in a future iteration, Miguel.
Okay, yeah, thanks a lot for the invitation. This was a lot of fun. Thanks.
Have it here. All right, everyone. See you at the next speaker series.
Okay, thank you.